Introduction to Signals, Part 1. So what is a signal? Signals are functions of independent variables that carry information. So the key point here, signals carry information. There are many types of signals. You can have it in terms of electrical signals, acoustic signals, video signals, and biological signals. For our course, of course, electrical signals would be more relevant to us. So the outline for this video, you are going to be introduced to the signal basic operations, the classification, and also the representations. So the first one, signal basic operation. We have scaling, inversion or reversal, and shifting. Time scaling. So if you have a signal at t is compressed in time by a factor of 2 denoted as yt, it means whatever happens in t at some instant t also happens in yt at the instant of t over 2. So consider a signal here. This is at t, your incoming signal. When it goes into a system, it will produce an output of yt in this case. So you have yt is equal to x2t, meaning that your input signal has been compressed by a factor of 2. When you have your output yt is equal to xt over 2, meaning that your input signal has been expanded by a factor of 2. Next, we have time reversal. When you have yt is equal to x minus t, this means that the signal yt represents a reflected version of xt about t is equal to 0. Please consider the triangular pulse xt as shown in this figure. Find the reflected version of xt about the amplitude axis through the origin. So you have an incoming signal xt in diagram A. You have to find when yt is equal to x minus t. This means that your input signal has been reversed or flipped. So what you have to do is just flip the signal. So here your t2 has become minus t2 and your minus t1 has become t1. Next, we have time shifting. If a signal at t is delayed by a period second, denoted as yt, it means whatever happens in t at some instant t also happens in yt. Period second later at the instant t plus period. So here consider an input signal of xt. When you have an output yt is equal to xt minus period, this means that your signal has been delayed by a period. When you have yt is equal to xt plus period, this means that your input signal has been advanced by a period. So these following are the basic signal operation that is usually used in the representation and processing of signals. You will have time shifting, frequency shifting, time scaling, signal addition, constant multiplication. These are some of the diagrams of basic signal operation. So the diagram A here is showing you an adder. When you have two signals xt and yt coming into an adder, it will produce an output of zt, which is the addition of those two signals. Diagram B is showing you a constant multiplier. Consider an incoming signal of xt going through a constant multiplier with alpha. So the output will be the multiplication of alpha and xt. Next, in diagram C, delay. So consider the incoming signal of xt coming into a system with delay, tau. So it will produce an output which is equal to at t minus tau. Finally, you have modulation. When you have one signal xt and another signal wt coming into a modulator, and it will produce xt times wt. You can also classify your signals based on the predictability of their behavior, time variable and their amplitude, energy content, repetitive behavior, and also symmetric. Size of a signal is a number that indicates the largeness or strength, or sometimes easier for us to understand is the signal amplitude. So you can determine the size of the signal based on two. First is signal energy and the second one is signal power. So signal energy can be calculated by using this formula. E is equal to the integration of x squared t dt from minus infinity up until infinity. While your signal power can be calculated by P is equal to limit from t nearing to infinity 1 over period, the integration of x squared t dt from minus period over 2 up until period over 2. So how do you differentiate a finite energy and a finite power signal? So a signal at t is said to be finite energy or energy signal if the signal is finite and integrable and the power is 0. On the other hand, the signal at t is said to be finite power or power signal if the signal is infinite and not integrable. As being told just now, you can classify your signals into different forms. So you will have continuous time versus discrete, analog versus digital, periodic versus aperiodic, energy versus power, and deterministic versus random. Okay, the first one, deterministic versus random signal. So a deterministic signal is a signal whose physical description is known completely, either in mathematical form or in a graphical form, whereas a random signal cannot be predicted precisely. So the first one, deterministic signal, is quite apparent to us. You can determine the physical description, but the random signal cannot be predicted easily. Next, we have continuous versus discrete. So continuous time can be specified for every value of time, while discrete time can only be specified for discrete values of time. So here you can see that a continuous time continues along the way, while discrete time can only be determined at only that specific time. Next, we have analog versus digital. So the analog signal is when the amplitude can take on any value in continuous range. A digital signal, the amplitude can take on only a finite number of values. So usually digital signal is denoted by binary numbers, which is 1010. You can actually change or convert an analog to digital or vice versa. So when you have an analog signal, you can easily determine the digital characteristic of that analog signal. Next, we have periodic versus aperiodic. So a periodic signal is a signal is said to be periodic if for some positive constant T0. So you have xt is equal to xt plus T0. So in other words, a periodic signals repeat with some period t. So if you see a signals that keep on repeating, then it is periodic. Otherwise, it will be aperiodic.